You might think that we have enough water on Earth. Our planet is over 70% water by volume, but most of that water is actually salt water. Fresh water, which is critical to all life, is only a small fraction of all the water on the planet. Clean, fresh water is necessary for human survival. We need it for drinking, for cooking, sanitation, and hygiene. Water is essential to a prosperous society. We use it in industry, agriculture, energy production, tourism, and it also holds important cultural value. Fresh water shapes landscapes, supporting the physiological needs of flora and fauna, and providing critical habitat for many species. My name is Francis de los Reyes, and I'm a professor of environmental engineering in the Department of Civil, Construction, and Environmental Engineering. My research and teaching is on water, how we treat it for use and reuse, while protecting the environment and safeguarding public health. When thinking about access to clean fresh water, it's important to consider water quality. But what exactly is water quality, and how do we assess whether the quality of water is high or low? Now, you can think of water quality in terms of three properties: biological, chemical, and physical. For example, biological properties may include the presence of algae, the presence of harmful bacteria and viruses, or other aquatic organisms. Common chemical properties include pH, hardness, which is just the amount of calcium and magnesium dissolved in water, and the levels of heavy metals such as lead and other chemicals like chlorine, or fluorinated compounds such as PFAS. Physical properties of water include parameters such as color, conductivity, which is how well the water conducts electricity, and turbidity, or how cloudy the water is. Now, we should also consider the physical structure of a waterway and how water flows through it. These different physical, chemical, and biological properties are often used as indicators to assess the quality of water. Now, what levels are considered acceptable depends on a number of factors. Most importantly, the intended use of the water. So for example, water used for human consumption is held to higher standards than water used for irrigation, manufacturing, or aquatic habitat. We call this concept fit for purpose. These different uses typically have different standards set by policy and regulatory agencies, guided by best practices and the best available science. Water quality can be degraded because of pollution, the introduction of harmful biological, chemical, and physical components to water. A common example of a biological contaminant is E. coli, or other fecal coliform bacteria. These bacteria originate from agricultural runoff or human waste and can lead to gastrointestinal illness. A well-known example of chemical contamination is the introduction of lead into drinking water from corroding pipes, which can cause lifelong neurological and behavioral impacts. And finally, erosion can cause the physical transport of sediment and the contaminants in them into waterways, leading to turbidity and a damaged aquatic environment. The movement of pollutants is directly linked to the hydrologic cycle. For example, point sources of pollution originate from specific locations. Think of a pipe emptying wastewater into a river. Non-point source pollution comes from diffuse sources across the landscape. Think of runoff across a cattle feedlot or acid rain. Pollutants can persist or dissipate naturally and can move between bodies of water or between surface and groundwater. Water bodies with faster movement, such as streams and rivers, typically retain chemicals for shorter periods of time. This is called residence time, or the amount of time the water or pollutant is present in a given volume. Slower moving water sources, such as groundwater, are more likely to retain chemicals for longer periods of time. Considering the nature of the water source is therefore important in addressing the contamination. Human activities have greatly altered elements of the hydrologic cycle, increasing contamination frequencies and levels. Fortunately, solutions exist for preventing, mitigating, and remediating pollution that does occur. Many natural processes can improve water quality, such as sediment filtration and nutrient conversions by plants, fungi, and bacteria. For example, wetlands have the ability to slow down water, allow sediment to settle out, and nutrients to be processed by plants. Scientists and engineers have developed many technical solutions to address water pollution. One common example you're probably familiar with is the treatment of domestic and industrial wastewater in engineered reactors before it's discharged to surface bodies of water. Other examples include ecological engineering solutions for restoring degraded urban watersheds and pump and treat systems to remediate contaminated groundwater. Of course, preventing pollution and ecological modification in the first place is often the most cost-effective and impactful solution. We all have an important role to play in ensuring the protection and sustainable use of our water resources. Understanding water quality and quantity is critical to improving human well-being and quality of life.